In this slide, we'll examine again the discrete time Fourier transform equation. In particular, we'll take these 4 samples from time 0 to 3, and this is of course aperiodic because after that all values are 0. Similarly, on the right hand side, it looks very much like the same signal. However, it is now periodic with period n equals to 8. So the periodic sequence repeat every 8 samples. Now, you will realize that because of the equations, if we are going to analyze discrete time Fourier series, we'll use this equation. And for discrete time Fourier transform, we'll use this equation. Interestingly, because the signal has only support from 0 to 3, 0, 1, 2, 3, then you realize that isn't this very similar to here as well? So these values that we compute are almost the same. There's some differences between the omega that we'll use. So let's go through and see what is the key difference in this slide. Alright, let's do the aperiodic first. So to work out x of omega, what you can do is to write an equation, a computer program which substitute x of n equals to 1 for these 4 samples of n equals to 0 to 3. What you then need to do is to write a for loop from 0 to 2 pi. Maybe you will say the interval you are interested in is, for example, small step is equals to 0.01 pi. And then you can then for every step you substitute omega into here and you generate the value. Well, what you will get is from 0 to pi, 2 pi, this is the omega, you'll get some values. And depending on how fine it is, then you can draw this shape. Now, what happened if you are decided to go from 2 pi to 3 pi? You'll realize that when you do that, the x omega repeats. So actually it is the same as this guy. So from 2 pi to 3 pi is the same as 0 to pi. What about the other way around? What about going from 0 to minus pi? Well, let's shade it in orange now. 0 to minus pi is the same as from 2 pi to pi. So that is why we either plot from 0 to 2 pi or from minus pi to pi, because this x of omega is periodic with 2 pi. Now, x of omega is a complex number. So typically, we have to plot both the amplitude in this example as well as the phase. So we have 2 figures, one plotting for the amplitude and one plotting for the phase. Now you see that x of omega is continuous. So to reconstruct x of n, we have to do the integration of from, in this example, minus pi to pi, or you can do from 0 to 2 pi. It doesn't matter. And you use this x omega multiplied by eij omega n d omega. You integrate, divided by 2 pi, you get the original sequence x of n. Now, let us go and see what happened when we analyze the periodic version of this signal. Here, there is only 4 samples and 0 everywhere else. Here, there's 4 samples, 0 samples, 4 samples again, 4 0 samples. So this period is x of n equals to x of small n plus 8. Is periodic 8. Now, since it is sample period 8, we only need to analyze from 0 to 7. Okay, because we only have to take in 8 samples, 0 sample to the 7 samples. So this is what the equation says. You want to analyze this signal, you only need to take the first period from 0 to n minus 1, which is n is 8, so it's 0 to 7. But of course, in this example, only the first 4 samples are non-zero. So actually, this is also, in this particular example, we only do 0, 1, 2, and up to 3, because only from 0 to 3 are non-zero. Okay, I mean you can do up to 8, but it's 0 multiplying by all these values, which is 0 anyway. Alright, the other key idea we have is this guy here. The signal, the complex exponential, must be e to the power minus. So this is I, sometimes we use j, doesn't matter. The key idea is that we have something called omega naught, the fundamental frequency, which is 2 pi over big N. And in this case, the big N is 8. So pi over 4 is the fundamental frequency, radian per sample. Now, you realize that it multiplies by k. This k here is the same as this k here, and k will range from 0 to n minus 1. So you realize that we are analyzing this xn using different complex exponential at different harmonic. The last little n here will generate the sequence for you. And finally, different to the discrete time Fourier transform, we have 1 over n here. So you realize that this guy and this guy here, they will generate the same value, except ck will have 1 over n. Alright, let us see now what happens. This is ck's. This is C0. This is C1, C2, C3, 4, 5, 6, 7. And what happened at 8? C8. C8, isn't it the same as this guy? C8 is the same as C0. C0 is 0. C8 is at 2 pi. Oh, okay. And we draw that little shaded little figures around it, and it looks exactly the same as x omega. So you can now think of the discrete time Fourier series as a sampled version, because we're only sampling at different frequencies, of x omega, and in addition to that, it is scaled by 1 over n. In this case, it's 1 over 8. So the value here is 0.5, and 0.5 times 8 is 4. So the value here is exactly 4. Now let us interpret ck. What does C0 mean? C, the index 0, it means at frequency k times omega naught. What is k? K is 0. 0 times omega naught. What is omega naught? 2 pi over n. And in our example, our n is 8. So it is 2 pi over 8 times 0. Of course, is 0. So C0 represents the 0 frequency. What about C1? K equals to 1. 1 times omega naught. 1 times 2 pi over 8. Pi over 4 radian per sample. What is pi over 4? 0.25 pi. So this C1 is sitting at 0.25 pi. Let's go back and look. 0, and here is pi. Here is half pi, and here is 0.25 pi. You look up, this value is exactly the same as this value here. Okay. And now let's look at C2. C2 is equals to 2 times 2 pi over 8 is equals to pi over 2. Pi over 2 lands exactly at the now. So this C2 is at the now. So now we can interpret what does CK means. Here, the K is the Fourier coefficients at the k omega naught frequency. Again, CK is a complex number, very much the same as x of omega. You have its magnitude and phase. The difference now is clear between discrete time Fourier series and Fourier transform. It is a sampled version of the frequency of x omega sampled, because we are only sampling at different frequencies and they are at fixed interval of k omega naught. And not only that, the amplitude is scaled by 1 over n. Now, once we have CKs, of course, we can now reconstruct it. And CKs are discrete. We only need to use k equals to 0 to n minus 1, because you see that it actually is repeating. From C8, you go to C9. C9 is the same as C1. C10 is the same as C2. What about C minus 1, which is here? C minus 1 is the same as C7. So this guy here is the same as this guy. This guy here is the same as this guy. So you now see that it is periodic with n. Once we have CKs, we only use the first n of them, k equals 0 to n minus 1. We multiply CK by positive EI plus 2 pi over n kn. Positive complex exponential compared to this guy rotating different ways. This guy is rotating clockwise. This guy is rotating anti-clockwise. We are multiplying CKs with this complex exponential. When we sum them up, we'll get xn again. So I hope that this picture here gives you a detailed explanation and differences between DTFS and DTFT. Thank you.